Okay, so integration by parts. Now I'm going to start this off by doing a quick review of the product rule. So recall the product rule says the derivative with respect to x of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x. All right, that's the product rule. Write that down. Yeah, you know it, I know. But it's going to build into the proof for integration by parts. So let's integrate both sides of our equation here. Right, so if I integrate this side, I can integrate each part separately, right? So because it's addition. Okay. Now, I'm going to manipulate this equation just one little thing. I'm going to take this plus g of x, integral of g of x f prime of x, and subtract it from this side, from both sides, really, right? And so I'm going to have this integral, the integral of f of x, g prime of x, equals the integral of this, the integral of d dx f of x, g of x, minus the integral of g of x f prime of x. So again, all I did was I subtracted this guy right here from both sides, and I just rewrote it with this on the left side. Okay. Now, what is the integral of the derivative? Just this, right? Just the function. So we have the integral of f of x g prime of x equals f of x g of x minus the integral of g of x f prime of x. Now this is what we call integration by parts. Now I'm going to simplify it a little bit using u and v. I'm going to say let's let u equal f of x and v equal g of x. Okay. If I take the derivative of u, I'll call that du, we get f prime of x dx, out of space. And if I take the derivative of v, I get dv, which would be g prime of x dx. And so coming back up to this statement right here, this would equal the integral. Well, f of x is u. G prime of x dx is dv. So the integral of u dv is equal to f of x g of x, well, that's uv, minus the integral g of x is v, and f prime is du. This is going to be our formula for integration by parts. The integral of u dv equals uv minus the integral of v du. That's our correct play. So that's going to be our formula. That's going to be what you're expected to just kind of know, believe it or not. Depending on where you go and who your professor is and stuff like that. But it's definitely in the book and stuff. But, okay, so integral of u dv equals uv minus integral of v du. So let's do some examples of how we apply this. So, example 1. Let's say I want to integrate x times cosine of x dx. Now notice if we tried our normal integration process, we would say, well, we've got cosine of x, right? The integral of cosine is sine. But that x just, you can't do anything with it, right? And we can't integrate them separately because it's multiplication. And we'd have to worry about the product rule, right? If we did in other words, if we just said, oh, this is x squared over 2 times the sine of x, right? Well, if we take the derivative of this, we would use the product rule, and we definitely aren't going to get back to this. All right, so we can't do that. So we have to use integration by parts. So I'm going to say, it's an x. I'm going to start by saying, you know what? Let's let u equal x. Okay. I'm going to say, let's let dv equal cosine of x dx. Now, if I take the derivative of x, what do I get? 1 or just dx. And if I know that dv, if I know the derivative of v is cosine, then v must be sine. So let's write down our formula for the integration by parts. So the integral of u dv equals uv minus the integral of v du. Now notice what I've done here. I made part of my integrand, the x cosine x, my u. I made xu, and I made the other part dv. Right? So now this is this, which means that if I integrate, I have to get this. Okay. So the integral of x cosine x dx equals, well, my u, coming back over here, the reason I filled this out, u was x, v was sine x. So uv would be x sine x minus the integral of v du. Well, v was sine of x, and dv was dx. Now notice what's happened here. Can we integrate sine of x? Sure. So we've got x sine of x minus, what's the integral of sine of x? Negative cosine x, so this becomes plus cosine of x plus c. And we've just integrated a previously unintegrable function. Something that we couldn't have done before. Now we can integrate. Let's do another example. Everybody got this? Example 2. So I've got the integral of x squared e to the x dx. Okay. Now again, if we just try to integrate this, we've got a problem because we have multiplication, and we can't integrate x. We wouldn't get x cubed over 3 times e to the x, because then we'd have to use the product rule to take the derivative. We don't get back to this. So let's let u equal x squared and dv equal e to the x dx. So what is du? So 2x dx. And then v? Well, for the derivative of v is e to the x, and the function itself must have been e to the x. Okay. And so again, writing down my u dv equals uv minus the integral of v du. And you may be wondering, do I need to write that every time? And I'm going to say yes, so you'll remember it. You write it every time, you'll remember it. It kind of rolls off the tongue once you say it a few times. But it's also easy to get backwards, so you want to write it every time. Okay, so integral of x squared e to the x dx. Notice again, I chose my u and my dv, so that I've got my x squared is u, e to the x dx is dv. So my uv, well, u was x squared, v was e to the x, minus the integral of v, so that's e to the x du. So I'm going to write that as 2x e to the x dx, just to kind of put it in that normal order. What's up?
Does it matter which one is u and which one is v?
It's a great question. Yes, it absolutely matters. Okay, so 2x e to the x. Well, we've got a similar problem right here. Right? We can't just integrate this because there's that x hanging out. So think about this. Let's let u equal 2x, dv equal e to the x. So what's du? So 2 dx, and then v would be e to the x. And so following integration by parts again, I'm not going to rewrite the formula, right? But following integration by parts again, we get x squared e to the x minus, okay. Now we have uv, right? So 2x e to the x minus the integral of v du. Oh, well, now we just have 2 e to the x dx. Now, can we integrate 2 e to the x dx? Sure, the 2 is a constant, so we can just imagine sign in there, right? Just right at the end. And so now we've gotten this where we can integrate. And so we have x squared e to the x minus, I'm going to distribute this negative. I put parentheses on purpose, by the way. That's because this minus, I'm subtracting whatever this integral is. And this integral is this integration by parts again. And so I'm going to distribute that negative. So I have 2x e to the x minus a minus is a plus. And the integral of 2e to the x, well, that's just 2e to the x plus c. And so sometimes integration by parts doesn't work the first time. Yeah. It's like a lot of things in math where we just have to, if it doesn't work the first time, it's iterative. You can do it again and again to your new answer. Now, Jerry asked a really good question. He says, does it matter which one is U and which one is V? So let's, for example 3. Very good. For example 3, let's do this problem again. And this is, I'm going to call it non-example 3, actually. But, so integral of x squared e to the x dx. And this time I'm going to say, you know what, let's let u equal e to the x and dv equal x squared dx. In other words, I'm going to do it the other way. So what is du? Okay, e to the x dx. And what is v? In other words, it's the function x cubed over 3. Okay. So let's see. Integral of u dv equals uv minus the integral of v du. All right. So the way that we've chosen our u dv here, if I do uv, we get x cubed over 3 e to the x minus the integral of v, which is x cubed over 3, e to the x dx. Well, maybe like last time. Maybe okay. Let's continue. All right, we can't integrate this. Let's try. Okay, so let's let u equal e to the x. dv is now x cubed over 3. So du is e to the x dx, and v would be x to the 4th over 12. And so we have x cubed over 3 e to the x minus uv, so that's x to the 4th over 12 e to the x minus the integral of x to the 4th over 12 e to the x dx. So what's happening here? It's getting bigger and bigger. It's not simplifying down to something we can integrate. It's going the opposite direction. So that's why I call it a non-example. That tells me I picked my u and my v wrong. And we'll talk about how to optimize that with that choice in just a few minutes. Okay. So this is going the wrong direction. I say I must be picking my u and my v backwards. And so let me try flipping them around and see what happens, and it'll reverse. Okay. Where it doesn't simplify at all? Yeah, absolutely. It's entirely possible, in which case the function may not even be integrable. Not every function has an antiderivative, so it's entirely possible you could be given a problem where you can't do it. Okay, example 4. So this one we'll do another example. So let's say I want to integrate x times the natural log of x. Now that's looking closer to the beginning problem, right? The integral of ln of x. This is close, x ln of x. So I'm going to say, you know what, let's let u equal, what do you guys think? What should we let u be? X. Okay. So dv would be ln of x. So what's du? 1 dx. And what's v? Well, v is the integral of ln of x. We've already kind of figured out we don't know that. All right? So we don't know the natural log of x, so we must have picked a bad u and v. Okay, so maybe, by the way, rather than erasing on your paper, you may consider just crossing out, writing no bad uv, right? Because you don't have any record of why you erased. Did you make the mistake, or was it a learning experience? This was a learning experience. We chose a bad u and v. So what does our u have to be then? It must be ln of x. dv must be x. So now what's the derivative of u? What's du? Jonathan said earlier, 1 over x. And the derivative, the integral of x would be x squared over 2. Okay. Now you may be thinking, well, that's not going to simplify. Well, let's just see what happens. So the integral of u dv equals uv minus the integral of v du. All right, notice I write that down every time. It's finally, hopefully, stick in my brain a little bit. uv. So that would be ln of x times x squared over 2. Right. So I'm going to write that as x squared over 2 times ln of x. It doesn't really matter, but minus the integral of v du. So I've got x squared over 2 times 1 over x dx. Right? So x squared over 2 ln of x minus the integral. Now x squared over 2 times 1 over x, well that simplifies. Right? The x's will divide out and we're left with just x over 2. Can we integrate x over 2? Sure. Right? It's fairly straightforward polynomial. So x squared over 2 ln of x minus, what's the integral of x over 2? Add 1 to the exponent, we get x squared. Divide by that exponent, we get 4. Let's see. So the choosing the right u and v is the difference between being able to do the problem and not even getting the wrong answer. I mean, not even being able to do it. Right? If you choose the wrong u and v, you can't do the problem. Okay. And so there's this overarching question: how do we pick u? How do I pick u? That's a weird question, Mark.
It looks like a smiley face.
Okay. So, in general, I'm going to write this sentence out. In general, we want u, I'm going to underline it with one line, to be something that simplifies when we find its derivative. So when we differentiate. Okay? So we want u to be something that simplifies when we differentiate it. Okay? Because we're going to find du. Likewise, we want dv to be something that remains manageable. When integrated. Okay, so we have 2 lines. So dv remains manageable when integrated. Not necessarily simplifies, but it doesn't. If u is simplifying and dv is doing something wacky, not helpful, and vice versa. If u doesn't simplify at all and dv is manageable, well, if u is not simplifying, then nothing good's going to happen out of it. So we need both of these things to happen. So there's an acronym you can use to kind of think about this. Your first priority. So priority, oops, I blew at the very top there. Priority for you. You guys need to go back a page? Okay. There you go. So in general, we want u to be something that simplifies when we differentiate it, and dv to be something that remains manageable when integrated. Okay. So priority for u. The first thing, if it's there, natural log. If there's a natural log there, that's your u every time. Why? Because the derivative of that is 1 over x. That's a lot simpler than the natural log of x. Okay? Your next is inverse trig functions. Okay? And you may be saying, well, why? But if you think about it, if we take the derivative of inverse sine, we get 1 over square root of 1 minus u squared, or whatever, right? Which is much simpler than inverse sine. Okay, it's still complex, but it's much simpler. It's something we can work with. Next priority is polynomials. So if there's no natural log, there's no inverse trig, your next choice for you is a polynomial. Okay, now the derivative of that, of course, gets simpler, right? I mean, the derivative of 3x squared is 6x, the derivative of 6x is 6. So that'll go down to some constant level where it integrates. If you don't have any of those exponential functions, so e to the x, but again, if e to the x is our u, the derivative of that is going to be e to the x, e to the x, e to the x. It doesn't simplify. So that's a last-ditch effort. And the very last thing you would choose, and really it's these two together. I shouldn't say it a lot. It's those two together. Just plain trig functions. Because we take the derivative of a trig function, we get another trig function. Take the derivative of that, we get back to the original one. Derivative of that, we get back, just keep going back and forth. It doesn't simplify. So if we're doing integration by parts, these last two will almost never be your u unless there's some other trig going on. Maybe there's two trig functions, and then you would have to make one of them your u and one of them your dv. Then it's a matter of just seeing which one works out. Okay, so this, notice, spells lipid. Not a word, but it's easy to say.
It is now.
Okay? So lipid. So when you're trying to figure out your choice for u, not for dv, for u, it's lipid. Once you know u, then the other one's dv. Okay? It's like PEMDAS. Okay. So let's go back to our initial question. It said, what's the integral of the natural log of x dx? Okay. Now, based on lipid, what's my u? Well, and what's the only thing that's left? Dx. Right? So dv is dx. So what is du? And what is v? The integral of dx is x. Okay, so using our integration by parts, the integral of u dv equals uv minus the integral of v du. U, that's ln of x. V was x, so we have x ln of x minus the integral of v du. So that's x times 1 over x. And by the way, when I write du, I always mean dx there. So x times 1 over x dx. So x times 1 over x, that's just 1. And what's the integral of 1? So x ln of x minus x plus 3. So as Jerry so eloquently put it about 5 minutes ago, the integral of ln of x is x ln of x minus x. But this is 1. Okay? So if you throw in the calculator, it gives that to you every time. Promise. Okay? So your assignment on this is going to be page 346 in your books, numbers 1 through 10. On the section 6.3 exercises. So section, don't do the top. Like the top has like the review part. So section 6.3 exercises. Number 1 through 10. Okay, so if you don't have your book here, that's fine. Sit with someone who does. It's been a while since we used the book, so make sure you find it, because Mr. Vela is going to want to start taking them up pretty soon. That's the other reason I want you to start using them, because in a couple weeks we're going to be turning them in. Remember, the answers to the odd problems are in the back of your book, and your calculator will do every single one of these without a problem. So you can always check your answer in the calculator. The answer in the back of the book will be the ideal format. It should be similar to the calculator, right? But you may see a few small differences. Okay, so you should be checking your answers as you go, especially at first. You should be writing down this formula for integration by parts every time. Okay, write it down every time. I know you have it at the top of the paper. Write it. Remember it. Okay.
I did want to